Hello, grade 11s. Welcome back to the channel Science Therapy. In today's lesson, we're going to be looking at chemical change, those endothermic and exothermic reactions. And without any further ado, let's look at this question 6 that we have here. So it says chemical cold packs are often used to reduce swelling after an athletic injury. A common example of a chemical ice pack is one that contains water and a packet of ammonium chloride. The cold pack is activated by breaking the barrier separating the water and ammonium chloride, allowing them to mix. The diagram below represents the potential energy changes when a cold pack is activated. Then 6.1 says, is this an exothermic or endothermic reaction? So while reading the statement, we can agree that there are some keywords that suggest to us that what type of reaction that this might be. So we have the keyword here, cold. So we are told that this is a cold pack. And then we know that what reaction is associated with cold is the endothermic reaction, because the endothermic reaction is the one that absorbs heat or energy. So this one, we say it always absorbs heat, and then therefore it is associated with what? With cold surroundings. But with an exothermic reaction, it is associated with hot surroundings, because we say this one releases energy, right? So from just reading the statement, we can get the idea of what type of reaction is this one. But also looking at the diagram here, we can see that the energy of the products, if we say these are the products and these are the reactants, so always we know that starting with the reactants and then we produce the product. So looking at the energy of the product, we can say that the energy of the product is greater than the energy of the reactants, which also suggests to us that this is an endothermic reaction, right? So we will say this is what? Endothermic reaction. Then 6.2 says, give one reason for the answer to question 6.1. It is as simple as that. You say the energy of the product is greater than the energy of the reactants. Then 6.3 says, which letter on the diagram represents the activation energy? The activation energy of the forward reaction. We know that the activation energy is the energy all the way from the reactants, the energy of the reactants, to the activated complex. And the activated complex is that maximum energy there. So here we have the activated complex, and then the forward reaction is this one. So starting from the reactants all the way to the activated complex, we can see that that length there is represented by C, right? So the letter that represents that is C, 1 mark. Then 6.4 says, explain how a catalyst would affect the activation energy, right? So we know what is a catalyst. We say a catalyst is a substance that speeds up the chemical reaction by lowering the activation energy. So that's the effect that the catalyst have on the activation energy. It lowers the activation energy and provides an alternative pathway for the reaction. So we say it would lower the activation energy by providing an alternative pathway for the reaction. Then 6.5 says, explain why a cold pack would be effective in reducing swelling after an individual had twisted his or her ankle. Refer to the kinetic molecular theory in your answer. So to explain that, we simply say, the cold decreases the kinetic energy of particles, right? So remember, when we speak of the kinetic energy of particles, we know that the temperature is defined as the average kinetic energy of particles, right? So we know that temperature is directly proportional to the average kinetic energy of particles, right? So temperature is directly proportional to EK average. So that means by simply decreasing the temperature, we are also decreasing the average kinetic energy of the particles. So in so doing, we slow them down, thus reducing the volume they will take up and this is effective in reducing swelling. Okay, so now let's look at another question. We are given the balanced equation for the reaction of carbon with steam is as follows. So this is our question 7. So this is carbon reacting with with water in a gaseous form. So this is water vapor. So carbon in solid with water vapor to produce carbon monoxide and hydrogen gas. Then they say the graph below, not drawn to scale, represents the change in potential energy of the substances during the reaction. Now 7.1 says define the term heat of reaction. So we know heat of reaction is also known as the enthalpy change. So sometimes they might say define enthalpy change. Know that it is the same thing as heat of reaction. So heat of reaction or enthalpy change is the energy or heat released or absorbed in a reaction. So we say released or absorbed because if it is an exothermic reaction, we know that the heat will be released. But if it's an endothermic reaction, we know that the heat will be absorbed. Okay, then 7.2 says, is the reaction endothermic or exothermic? Give a reason for your answer. Now, looking at the graph once again, we can see that these are the products. We can even tell from this equation here. So these are the products and these are the reactants. So these are the reactants starting off here and then forming the product. But then looking at the energy levels here, we can see that the energy of the product is higher than the energy of the reactant. So energy of products greater than the energy of the reactant. This suggested that this is an endothermic reaction once again, right? Why? Because energy of the product is greater than the energy of the reactants. Then 7.3 says use the information on the graph and write down the value of the activation energy. Now the activation energy, once again, we know is from the activated complex, which is this maximum energy here, all the way to the energy of the reactants. So to calculate the activation energy here, we need to say 593 minus 49, right? So let's quickly use our calculator for that one. So 593 minus 49, this gives us 544. So 544 kilojoules per mole, right? So be mindful of this SI unit in here. And then heat of reaction, the heat of reaction, we know that, so this one here represents the activation energy. And this here, the difference between the energy of the product and the energy of the reactants, this represents your enthalpy change, right? Or the heat of reaction. So we just simply say, what is the energy of the product? It's 180. Then energy of the reactant, it's 49. So 180 minus 49 will give us the value for the enthalpy change, which is 131 kilojoules per mole, right? So that's it. Now, let's look at another one. So again, here we are given cold packs and hot packs. They say cold packs and hot packs are commonly used to treat injuries to reduce swelling in muscles. Study the reactions taking place in the packs and the graph below and answer the questions that follow. So we are given the cold pack with this reaction here. So we know once it says cold pack, this is obviously an endothermic reaction. And then this is a hot pack, which is obviously an exothermic reaction. Then we are given this graph here. So we can see that this graph here includes this broken line here, which indicates the effect of the catalyst. Remember, I said every time you have this represents the effect of the catalyst, because the catalyst, what does it do? It lowers the activation energy. So if you can look at the distance from here all the way up there, and then look at it in reference to this graph with the broken lines, you can see that the activation energy has now decreased. Then 6.1 says define the term activation energy. How do we define that one? We say activation energy is the minimum energy required to start a chemical reaction. Then 6.2 says provide values from the graph for the following. Then 6.2.1 activation energy for the reaction in the absence of a catalyst. So without a catalyst, right? So what do we do for this one? Now, look at the blocks here. Because we are given this, you need to find the interval in which each block is representing. So from this one, we can see that we have 0 to 10, but how many blocks are in here? It's 1, 2, 3, 4, 5. So we just say 10 divided by 5, and this will give us that each block here is representing 2 units or 2 kilojoules, right? So that means this is 0, 2, 4, 6, 8, 10, like that. So if we are looking for the activation energy, that they say give us the value of the activation energy in the absence of a catalyst. We know that the activation energy has to be from the activated complex minus the energy of the reactants here. So this is the reactants. And then look now, what is the value in here? Let's count the blocks. It's 1, 2, 3, but each block is representing 2 units. So 3 blocks will be representing 6 kilojoules, but then add that to 60. So we have 66 kilojoules. So it's 66 minus 10, and this will give us 56 kilojoules. And then 6.2.2 says the energy of the product. What is the energy of the product? So let's look at the product here. We have it right here. But then let's count the blocks. It's 1, 2, 3, and each is representing 2 units. So what do we have below here? 30. So that's 30 plus 6. This would give us 36 kilojoules, right? And then enthalpy change. For the enthalpy change, we know this is energy of the of the product minus the energy of the reactant. What do we have as the energy of the product? It's the 36, and then minus the energy of the reactant is 10. So we have 26 kilojoules, right? So 6.3 says, does the graph represents the reaction for the hot pack or the cold pack? Give a reason for the answer. Now let's look at this. We already identified that the cold pack would be an endothermic reaction, and the hot pack would be an exothermic reaction. Now, looking at this graph here, we can see that the energy of the product is greater than the energy of the reactant, which suggests that this is an endothermic reaction. So looking at this, we can see that which one corresponds with the endothermic reaction. It's definitely the cold pack. So this graph represents the cold pack. Then 6.4 says define a catalyst. What is a catalyst? We say a catalyst is a substance that speeds up the chemical reaction by lowering the activation energy. 0.5, the reaction mixture is heated. How will this affect the activation energy for the reaction at this higher temperature? Choose from increases, decreases, or no effect. So they say the reaction mixture is heated. How will this affect the activation energy? So we know exactly here that this will be no effect. Why no effect? Because the only thing that can affect the activation energy is the catalyst. So the catalyst is the only substance that will have an effect, or the only change that will have an effect on the activation energy of the reaction. So the answer there is no effect. Okay, so let's look at this question 6 here. It says the diagram shows the potential energy changes during the following chemical reaction. Then 6.1 says define the term activation energy. Once again, what is activation energy? We say activation energy is the minimum energy required to start a chemical reaction. So by the by how frequently this definition is appearing, you know very well you shouldn't walk into an exam room without knowing that definition. Then 6.2 says, is the reaction exothermic or endothermic? Give a reason for the answer. Now let's look at this one. We can see with this one, these are the reactants, and this here are the products. So looking at this graph here, is it exothermic or endothermic? We can see that the energy of the reactant is now greater than the energy of the product, or you can say energy of the product is less than the energy of the reactants. So therefore, this is exothermic reaction. So this is exothermic reaction, and give a reason for the answer. We say energy of product is less than the energy of the reactant. So there you go. Exothermic energy of product is lower than the energy of reactant. Now, 6.3 says, what is the total bond energy of H2 and Cl2 of the reactants? Give a reason for the answer, right? So let's look at this. Here we know that we have what? We have the reactants, and then down here we have the products. Now the question is, what is the total bond energy H2 and Cl2 of the reactants? But here they're asking about bond energy. What is bond energy exactly? We say bond energy is the energy that is released, when bonds are what? Are broken. So this is the energy released when bonds are broken. So okay, now let's see this. This is similar to what we would define as, remember, energy released when bonds are broken. But what is activation energy? We say this is the minimum energy required for a chemical reaction to start, right? So we know that a chemical reaction will start when the bonds are already broken. So there's a link between the bond energy and activation energy. We can pretty much say that the bond energy is the same as the activation energy. So in other words here, what are we looking for? We are looking for the activation energy, which is already indicated here. Remember, the activation energy of a exothermic reaction is all the way from the reactants to the activated complex. This is what is showing you the activation energy. So for this part here, you only need to say 679.1 kilojoules per mole. And then what is your reason? You say this is the energy released when bonds are broken, which is similar to activation energy. Then 6.4 says determine the energy released by the bond formation of the HCl molecule, right? So from here, we can see that we have the activation energy, right? So when bonds are broken, we have this energy that is being released here, which is the minimum energy needed to start the chemical reaction. But after the chemical reaction is started, we need the energy to convert the reactants or to turn those reactants into products. So the two energies that are involved here is the activation energy and the enthalpy change. So to find the energy released for the bond formation, we simply need to add these two energies. So we will say, what is it that we have there? 679. So let me do it here. 679.1 plus 184.7. So when we add this to 679.1 plus 184.7, we get 863.8 kilojoules per mole. But then you will note something here. They said, determine the energy released by the bond formation of the HCl molecule. So here they are concerned about only one HCl molecule. But from this reaction here, we can see that two molecules of hydrogen gas plus one molecule of chlorine gas forms two molecules of hydrochloric acid, right? So, but then here we are only concerned about one hydrochloric molecule. So that means this is the energy involved in forming two hydrochloric uh, acid molecules, but we only need one. So we'll say HCl, only one molecule of HCl will be 863.8 divided by 2. Because remember, this represents the energy released to form two molecules of hydrochloric acid, but we only want the energy released to form one hydrochloric acid molecule, right? Then that divided by 2, this will give us 431.9 kilojoules per mole, right? And that becomes your solution for 6.4. 6.4. Okay, so 6.5 says, what effect will the addition of a catalyst have on the value of 184.7 kilojoules per mole? They say write down only increase, decrease, or no effect. Give a reason for the answer. So what will happen here? We know that when you add a catalyst, the catalyst only has an effect on what? So they're asking on this value here. What is this value? We said this is the enthalpy change. We know that the catalyst does not have any effect on the enthalpy change because the catalyst only has an effect on the activation energy. So the function of the catalyst is to lower the activation energy. It does not do anything to the enthalpy change because it does not change the energy of the product nor the energy of the reactant. So it does not change the energy of the reactant. It does not change the energy of the product, meant to say. So that means it cannot affect the enthalpy change. So we will say no effect. The catalyst only affects the activation energy. Now let's look at this one, the last one for the day. So it says, learners study endothermic and exothermic reaction by conducting experiments 1 and 2, in which the reaction shown in the table below takes place. So we have experiment 1, we have experiment 2. Now note, there is nothing here that shows us that that suggests to us that either one of the reactants are exothermic or endothermic. That means there is no telling from just looking at the equation whether a reaction is exothermic or endothermic. They would have to give us further information. Now they say the learners measured the initial and final temperatures of the reaction mixture. They also obtained activation energies. They also obtained activation energies for what? So let's see for the reactions below from the data table, right? So now looking at this one, we can see that we are given now experiment 1 with an initial temperature of 24, but then a final temperature of 36 degrees. That means now energy increased here. So that means heat was released. Why is there an increase in temperature? Because heat was released. So you can see the activation energy is 75 kilojoules per mole. And then in experiment 2, we can see that the temperature was 24, but then it decreases to 18, but the activation energy is now higher. Now we know that this one would have hot surroundings. Exothermic releases the energy. This one from 24 to 18, cold surroundings. So endothermic reaction, it absorbs the energy. Again, you can tell from the activation energies. 75 is a lower activation energy, which is true for an exothermic reaction. It has lower activation energy, but 237 is a higher activation energy, which is true for endothermic reactions. Now, define the term activation energy. Again, we know what is that. So we say this is the minimum energy required, to start a chemical reaction. Then they say in which experiment 1 or 2 is the reaction exothermic. Now we know it is in experiment 1. Why is it so? Because we say it has what? Lower activation energy. So lower activation energy. Now, is the heat of the reaction delta H positive or negative for an exothermic reaction? It is definitely negative. We know that. Now they say write down the general name of a substance that can be added to the reaction mixture in experiment 2 to reduce the activation energy. It is definitely a catalyst, right? Then both reactions produce the same number of moles of oxygen gas. How does the mass of H2O2 used in experiment 1 compare to the mass of H2O used in experiment 2? So obviously this would have to be based on the molar mass. The molar mass for this one is way bigger than the molar mass for H2O, right? So if this one has a bigger molar mass, that means it also has a greater mass, right? So how does the mass of H2O2 used in experiment 1 compared to that used in experiment 2? It has to be larger than. Then draw a potential energy versus time graph for the reaction in experiment 2. The following must be shown on the graph: heat of enthalpy, heat of reaction, and then activation energy. So for that one, we know that we'll be drawing an endothermic graph. So there we go. So activation energy and enthalpy change. So that's the sketch. Awesome.